Okay, for those of you already here with us, so good afternoon, welcome back. If you've attended the other days, if you're only attending today, welcome to today's session dedicated to hydrogen. So, the title here, day 4, December 16th, we're going to talk about green fuel generation using renewable energy, H2 generation and synthetic fuels maybe. So I'll first present the team for those of you who don't know them yet. So I'm I'm chairing this session, should have been chaired by Brian, but unfortunately Brian can't make it. And then the rest of the team which helped organize this event are Carla Silva from CITEVE, Guilherme Gaspar from the University of Lisbon, and Paulo Ferreira from also University of Lisbon and IST. Our back office people, which have been extraordinary in really helping us out, getting the details sorted out, are Sheila Habib and also Vera Pinto. Very well, so today we have 1, 2, 3, 4, 5 speakers. We're really happy that managed to get such a list of interesting speakers for today. Depending on how long each talk will be, we can either have some questions asked at the end of the talk, or if we're running late, we'll push the questions to the roundtable at the end, where we have 30 minutes for that, for the discussion. Okay, so I'll move on to introducing our first speaker. Professor Upal Vijayanta is a professor of physical chemistry at Loughborough University in the UK, somewhere in the Midlands. His experience and expertise include industrial product development between 2002 and 2006, circular economy, low-cost, zero-carbon hydrogen, electrochemical energy storage, and energy materials. It's between 1995 and 2001, and then back to this between 2007 and today. He currently serves in 2 technical task groups of hydrogen technologies in the International Energy Agency, or the IEA, which is most commonly heard for. He is co-director of the UK EPSRC Centre of Doctoral Training in Sustainable Hydrogen. Those of you who don't know, the EPSRC is one of the main science and research funding bodies in the UK. It actually stands for English. I can't remember anymore. Anyway, it's the main supplier of funds for research. Recently, he led a large group of academics, over 300 industries and local government representatives to develop the UK Midlands Pan-Regional Green Growth Plan. Sounds exciting. He's advised on the recently unveiled UK hydrogen strategy to steer the government commitments to meet the net zero targets by 2050. He has served in industrial advisory boards and has worked as a project receiver and a panel member of funding agencies in many countries. Aside from that, he's published hundreds of papers and has many PhD students come out of his labs. So, without further ado, his talk will be on hydrogen production to meet decarbonization. Upal, the floor is yours.
Right, thank you, Killian. I guess you can hear me, right?
Loud and clear.
Right, there you go. Okay. Right, how do I get to this? Yeah, okay, good. Okay, thanks so much, Professor Killian, and really appreciate your kind introduction, and welcome to everybody. And I'm quite excited about sharing some of the work I've been doing over the years in this space, and then give you some of my thoughts. May or may not be agree with you, but the whole idea of these meetings and these workshops are that basically you come up with and share your thoughts and ideas and based on your experience and expertise, and then discuss with others. So I just wanted to acknowledge some of the colleagues and RAs and students, external stakeholders, sponsors, and many other colleagues who being provided critical and constructive feedback for many years for the work we have been doing, which has been tremendously helpful. I'm not going to too much details and names here because it's too much to mention. The reason why we are here today, we're all here today, and we are concerned about in this space is a significant amount of greenhouse gas emission by man-made activities, causing irreversible damages to our Earth for many years. And one of the sectors, many sectors listed in here in this important report, Hannah Richie's co-authored this report in 2020. As you can see, the energy space or energy mix is significantly responsible. It's about 73%. There are other areas responsible as well, but as people who work in and interest in energy, this is something alarmed to be about. Now, I've taken this again from my IPCC report, one of the recent reports. You can clearly see that how much we have influence, our influence, impact on global temperature. So clearly, I can see the nice correlation. You would come with various theories and stuff, but at the end of the day, if you look at longer term, it's just clear that the fluctuations are there for if you take 10 years, 15 years, 25 years, and even 50 years, 100 years, you can see some fluctuations. You can build up many theories based on that. But if you look at the journey from 1850, it is absolutely clear that the correlation is there. Obviously, the temperature increase directly correlating to carbon dioxide emission, carbon dioxide concentration, which is one of the greenhouse gases. There are the greenhouse gases as well. So when it comes to carbon dioxide, we know that different parts of the world responsible for emission of carbon dioxide, and then that depends on the time as well. For example, when we have the Industrial Revolution in Europe, and so Europe has been significantly responsible for carbon dioxide emission, but then when other countries picking up, and they became much more responsible for carbon dioxide emissions. So this is our journey, at least from these studies. So I don't know how to get rid of this. Yeah, okay. Right. Back in Killian mentioned about the industry, the work we've done in industry. So I worked, but not many people thought about hydrogen as a solution for energy need. Not many people believed. Around 2003, 2006, we have been doing an important experiment at industrial scale to see the photoelectrochemical hydrogen can be scaled up and at commercial level. So these are from lab scale from 2003 to prototypes developed in 2005, 2006 on different level. And then this involved collecting hydrogen and then various plumbing. And then, so basically these devices would generate hydrogen upon capturing solar light directly. It's different to PV plus electrolysis. This is combined device of PV electrolysis, but the device itself is slightly more complex because you call twin cell device. So you need a PV backup as well, and that's why you see some of the photovoltaic cells in this prototype demonstrator. And then obviously I left the industry. And then back in academia, I went back to a drawing board and look at some of the material challenges, and then from a more the surface termination and direction, material directional viewpoint, and then we studied the impact of material growth on generation of hydrogen. This is all documented here. What this tells is that basically you can control, you can develop a smart material to increase the generation of hydrogen from photoelectrochemical cells. This is our internal conversion efficiency again. Now, in another different task, I worked with a company called Intelligent Energy, and they have been developing a device called OP. And this is a photograph of this device. And this is a backup power source. You can see the USB connection in here. take the PowerPoint. So you can see the USB connection in here. So this it's basically if your mobile phone run out of power, or your laptop run out of power, this would give a backup. What we have here, we had in here, or company had in here, is the hydrogen and chemical hydrogen generation and the fuel cell kit. So when you need it, basically it's release a chemical, the hydrogen. This concept has also been looked at by the same company, even now, for drones and then surveillance missions and then delivery and transport and many other sectors as well. So this is not just a backup system. So obviously the key advantage of hydrogen is it has a greater energy density and can provide power for longer, as long as we have a stream of hydrogen. And in other words, fuel cell powered portable devices could be potentially last longer and provide that more power, provide more power per unit volume, unit weight. Now, I don't know if anyone can help me to get rid of this bar here. I'm just struggling.
We don't see any bar. Maybe
you don't see? Okay, right. I see.
No, we don't.
All right. Okay. Right. It's really annoying for me. Right. So one of the so I can't see the heading. Let me. Okay, that's fine. Okay. So one of the factors for us to consider is that at the moment, most of the hydrogen produced by SMR, a very small fraction produced by electrolysis. And these methods are appropriate for stationary generation, but they are not appropriate when you actually try to power a device and a mobile power device. And that's where you need basically portable onboard generation solution. So what we've done is with this company, we looked at the generation of hydrogen from various chemical generation of hydrogen. One of the chemical we looked into at that point is ferrosilicon. So ferrosilicon, when generate, when you add sodium hydroxide, and you could clearly see the generation of hydrogen picking up. And we identified 3 regimes, 1, 2, 3, which is induction, generation, and the steady state stage. And those stage basically we looked at in terms of activation energy and studied the activation energy. And then we found, using other chemical sources, the way to delay the hydrogen release and or increase hydrogen release and control the hydrogen release. So release hydrogen to fuel cell and control way to different missions. And if it's a backup power, it's one way. And if it's a drone mission with a, say, 4-hour mission drone, and then you could design with these chemicals and then release and so on. So it's an area that we looked at. And more recently, as Killian said, we looked at the green growth plan for the Midlands. And I want to share a couple of slides on here. I guess we discussed about the role of hydrogen in Midlands. It's not just in the UK, but it's not just the UK Midlands relevant, but this is relevant to many other regions in the world, depending on local scenario. Midlands is obviously a center of the UK. And we have quite a few major cities: Leicester, Nottingham, and Derby, and Birmingham, Coventry. It's in all about 300 companies and many academics and many stakeholders and government stakeholders as well. So one area we looked at is green building. When it comes to green building, obviously generation of low carbon heating is important. So in that sense, clearly there's a hydrogen for gas for heating. Hydrogen heating is quite relevant, and the growth potential here is significant to reduce the greenhouse gas emission, reduce energy demand, improve the security, and so on. And we estimated about this region alone about 30,000 jobs, and then significant economic benefits and carbon reduction, 1.8 metric ton carbon dioxide, and so on. And the net zero transport is directly related to hydrogen fuel cell or direct combustion hydrogen combustion engines to replace internal combustion engines. And this is space, again, you look at the potential reduction of greenhouse gas emissions, 8,000 jobs, and then 7 metric tons of carbon dioxide, and then significant economic benefits. And I will just keep these ones. I want to talk about number 5, yes, low carbon hydrogen. And here the generation and the infrastructure for heating and transport. And again, the focus here, our focus was to reduce the greenhouse gas emission and then quantify it with a 0.75 metric ton of carbon dioxide, and then the 14,000 jobs and so on. So I would skip this from this slide. I'm going to skip a few slides and move into my main point again. Right. Just remind ourselves that where we were obviously talking about the energy mix and the importance of curtailing carbon dioxide reduction. Now, the reducing the global carbon dioxide emission is concerned with the effort to limit the long-term increase in the average global temperature, obviously. This calls nothing less than a complete transformation of the way how we cook and eat, produce and transport and consume energy. And that means how we cook and eat and have a shower and then have to go on shopping or go to work and everything. So basically our behavior directly related. So the global pathway to net zero emission by 2050 is extensively described in one of the reports in IEA recently. And that's called Net Zero by 2050, a roadmap to global energy sector. And this requires considerable political consensus on reaching net zero. But the changes required to reach net zero emission by 2050 is poorly understood because it depends on, let's say, assume that we have 100% political will, which is never be anyway. There will always be people who argue against this. But let's assume that, but still, depending on our scenario today, depending on what we have around us, the pathway is very poorly understood. And that's why the green growth plans that we've done in the Midlands, studies like that for more regional basis, studies like that are important at global scale. And also in the UK, the Climate Change Committee released its 6th carbon budget last year, September, and provide the balanced pathways to reach net zero to the UK by 2050. So this reports and many other reports discuss the technology, economics, policy areas, and then suggesting obviously that integration of hydrogen into our energy mix will be a key factor to achieve the net zero. It alone wouldn't do that, but we need hydrogen integration to significantly reach that milestone, and we need many other help as well in many other sectors. Now, our report set out the steps needed to get the net zero emission by mid-century, 2050, or some countries targeting 2060, 2070, and we know that's all about politics. We need also say that about 197.6 million tons of blue hydrogen would be required annually, and that's need to come from natural gas or coal with the carbon capture and storage. And for me, I think, although this report says this, for me, I think I have a different twist to that. Probably you could look at, in addition to blue hydrogen, you can look at turquoise hydrogen, which I'll come at later stage of this discussion. I mean, the further 16 million tons of low carbon electrolytic hydrogen annually from electrolysis. And that needs to be powered by nuclear power, fossil fuel power plants, with CCS again. So in total, the report stated that 520 million tons of renewable and low carbon hydrogen need across a wide range of industries. Now, how would this compare to today's scenario? That's why I start with a couple of stars. So you have you have 87 million tons of largely gray hydrogen today. That's without any carbon capture, and that's coming from the gas and coal. And they mainly use in chemical plants and oil refineries. And that's because we don't have a hydrogen at scale high usage of hydrogen. We don't have a hydrogen economy yet. And that was the problem when we were in the industry as well, because nobody, even if we made hydrogen at that time at scale at very low cost, there wasn't anybody to buy hydrogen. But luckily, we can see that picking up gradually in the industrial sector. And then if the power to gas, heating and transport sector picking up as we expected, and if the fuel cell cost going down, and hopefully those sectors will pick up significantly, so that demand for hydrogen will be constantly increasing. So we can realistically hope for a hydrogen economy. And also 322 million tons of green and electrolytic hydrogen in 2050 would require a comparison, global electrolysis capacity of 3,585 gigawatts, up from 300 megawatts today. Obviously, there are gigawatts plants being designed, but they are still in the planning stage, unless anything that I'm not aware of being done elsewhere. And roughly, this is about 14,500 terawatt hour of electricity and about 20% of the world's electricity supply. So you can see the scale at where we, to achieve the net zero, and these numbers make clear sense that how far we need to move from today's scenario. Now, when it comes to hydrogen, this is really annoying that again, I can't see this top bit. Oh yeah, okay, I think I can pull it down. Okay, right, so when it comes to hydrogen, it's not just about the production, it's about transport and then transformation, and then until you get the end user and then efficient use and so on. So when you think about all that factors, it's become more complex. In fact, transport of hydrogen is even more complex than production. Really, probably the cracking step, if somebody can find a solution for that, the transformation to hydrogen economy would be much faster. But nevertheless, this focus of this talk obviously is that this talk and this workshop is that production of hydrogen. So let's focus on production of hydrogen. You can go on the spectrum, green hydrogen, stoppish hydrogens, yellow, blue, pink, gray, and all sort of colors. And there will be many more colors depending on the carbon emission as a carbon footprint. As I said earlier, gray and blue hydrogens dominate current production landscape. Now, if you think about the cost alone, without taking into account the carbon footprint, one of the key benchmark currently that we can say is the US DOE target that they said $2 per kilogram hydrogen by 2025 and $1 per kilogram hydrogen kilogram by 2030. And those need to come through net zero carbon pathways. So no gray, no blue, no gray definitely, but no blue unless you have CCS clearly embedded. Now, we currently are preparing a report on cost of hydrogen. It's being prepared, and hopefully it will be able to send this in the next couple of months. We look at the regional map of hydrogen and cost of hydrogen, and in the EU, US, China, and so on. You can see the current cost of blue hydrogen per kilogram is in the EU, and green hydrogen in the EU as well here, and the predicted cost, and then blue, and then predicted cost of green. You clearly see that if the prediction by 2030 works, and then you can flip the situation from blue to green, and so therefore more. This is a very helpful scenario for reduce our carbon footprint. The same here for US as well. And Japanese situation for green hydrogen is not quite clear, but they are quite heavily involved in blue hydrogen at the moment because of the significant coal that they get from Australia and other places. And you can clearly see the blue hydrogen, the cost reduction potential in Japan, in China. Again, we can see the same trend and global average. So if I take region by region, starting from EU. So the estimated cost for fossil-based hydrogen is about 1.5 euros per kilogram and 2 euros per kilogram with carbon capture and storage. And these prices vary among different countries in the EU region, of course. So assume the current gas electricity prices stay the same by 2030, which may not be. The EU predict that the low carbon fossil fuel based hydrogen would cost about 2 to 2.5 euros per kilogram, which is similar to current price. But the reason for this is that the EU is heavily investing in renewable hydrogen electrolysis and see the production of low carbon hydrogen as a short-term fix to reduce emission. But the electrolyzer hopefully will kickstart, and the so-called green hydrogen will be significant. And current cost of renewable hydrogen in the EU is about 2.5 to 5.5 euro per kilo. And that is cannot compete with fossil fuel or gray or blue hydrogen at all. And obviously anticipation is renewable. With the investment renewable will become more competitive. Electrolyzers will have will play a significant part, and therefore prediction for 1.1 to 2.4 euros per kilogram the target. And this is to produce 10 million tons of renewable hydrogen annually using wind and solar power. On the US strategy, of course, as we discussed earlier, and currently in US, about 95% hydrogen is produced by SMR, steam methane reforming with CCS. And this technology costs $2 per US dollars per kilogram. Sorry, it's in different units. We're talking monetary units we're talking about here. And then the target is to reach $1 per kilogram by 2030. So the cost of hydrogen, of course, highly dependent on the electricity cost and renewable electricity. The idea behind this is the renewable electricity will be cost competitive and then play a key role here. In the Japan hydrogen strategy, the Japanese organization METI, they have their roadmap for hydrogen, and the government want to reduce the production, of course, to brown coal gasification to US $1.34 per kilogram from the current several hundred yens per. It's not quite clear in US dollar terms, but 700 yens of Newton meter cube. And then obviously their roadmap, the METI roadmap, intend to reduce the cost of electrolyzers quite significantly by about fourfolds. Now in China, there's a study by McKinley, and they identified that renewable hydrogen production is already competitive with current methods of coal gasification with CCS. Now, this is a really encouraging situation because this is not something that anywhere else in the world we see. So that means that they have significantly reduced the renewable hydrogen production cost or electrolyzer cost or the solar cost or the wind energy cost. So that's really interesting situation. So the cost of coal gasification with CCS is approximately 2.8 US dollars per kilogram, with renewable hydrogen already low as 2.4 kilogram per kilogram. So you can see it's clearly the renewables winning, but the key underlying point, which I'll come later, is that the carbon footprint. And by 2030, China predicts that electrolyzers will be cheaper in all locations across China and will cost as low as 1.7 US dollar per kilogram, which is a lot cheaper than predicted 2.5 per kilogram for coal gasification with CCS. Now, one thing clear is that we could become net zero tomorrow in this part of the world and all the developing countries or developed countries, but the methane or natural gas business will move elsewhere by large companies, and they will keep selling natural gas and fossil fuel. And then these developing countries keep using fossil fuel. The global emission is a global issue. So although in Europe we could achieve net zero tomorrow, if say we could achieve that, it doesn't mean anything, because the problem is global. If Africa or Asia or Middle East keep emitting carbon dioxide, it doesn't help us. So here you can see that demand for methane has been increasing 10 to 15% on a yearly basis right now. And this is taken from World LNG report. It's a complex supply and demand landscape, and major production countries compete each other to grab the market share in developing countries. Basically, keep emitting carbon dioxide using fossil fuel. Here you can clearly see the growth, the methane growth business. So lots of LNG plants being built in developing countries right now. So really aggressively being built. And you can also see that transport of methane business is significantly strong. And you can see the annual growth is about 8.4 year on year. That's taken from the LNG report last year. So clearly something doesn't make much sense. Here we're trying to develop the green economy. We are trying to make hydrogen-based or hydrogen economy and make net zero, whereas in other areas, the fossil fuel based hydrogen mix, fossil fuel based energy mix is thriving. You can clearly see the mismatch. So one way to look at it is, while we're becoming net zero wherever we can, the political will and the economic support and the society, and then everybody work together to reach the net zero. We also need urgent solutions to decarbonize the fossil fuel-based energy sector. And that's part of the reason why I've paid my attention about 6 years ago to decarbonize methane base, basically convert methane to hydrogen and then capture carbon. So we set off our focus at the time, and this technology can produce so-called Tokus hydrogen, and then by methane pyrolysis. And you could pyrolyze methane or crack methane by various methods, which summarized in here, taken from the reports. You could do the I'm not going to too much detail. You could do plasma pyrolysis or fluidized bed or moving carbon bed or molten metal or molten salt beds. And we don't have much time to go into detail here, but you get the message. There are a number of methods you could follow for this case. Obviously, the key drivers for organic growth of hydrogen economy is the cost at end user point. That's including not the generation, the transport, and as well, and storage as well. The carbon footprint, so which we call the global warming potential, and the scale production. Because, as I said, we were developing photoelectrochemical hydrogen back in early 2000, but there's no chance for those technologies to meet the demands that we need, scale that we need. As I said later on, it is a massive scale demand we need if you were to make or kickstart the hydrogen economy. Now, this is an interesting, really interesting report recently published by Imperial College and Zurich group. And here they have looked at the total cost of production routes in terms of levelized cost of hydrogen. And they also taken into account the environmental impact, human health, ecosystem quality, and the resource depletion in this study. And then they looked at the SMR, methane reforming with carbon capture and storage. They looked at the methane pyrolysis and SMR alone, nuclear, wind, and then coal gasification, biogas, and then solar PV, biogas, and coal gasification without CCS and or carbon capture and storage, and with CCS. So clearly the the most cost-effective production route at the moment is SMR plus CCS. It's 4.67 US dollars per kilogram, according to their study. And the methane pyrolysis, as you can see here, offers the close cost comparative next route. It is 4.78 US dollars per kilogram. Now, what we know is that CCS is a still very early stage development. To get into a scaled CCS, we would expect another 15, 20 years of development. It's never going to happen in 2025 or 2030. Hope I'm not correct. I wish I'm incorrect, but if it's the case, then it will be great to see the CCS coming along. But there's science and experts indicates that CCS is not going to meet this target. There's a mismatch between the CCS and the hydrogen demand. So clearly the second leading contender here, the methane pyrolysis, has so much to offer. More importantly, if you look at the methane pyrolysis and electrolysis energy input, electrolysis requires about 200 megajoules. This is about 55 kilowatt power per kilogram of hydrogen, whereas for methane pyrolysis in comparison, it is 11 to 15 kilowatt hour per kilogram of hydrogen. So you can clearly see the benefit. If you make the renewable energy, right, then you can decide whether it's, if you have methane pyrolysis and electrolysis, you can decide whether it's really worth putting this electrolysis into renewable energy into electrolysis or methane pyrolysis, because you can get three times hydrogen by methane pyrolysis compared to electrolysis. And again, methane pyrolysis do not emit carbon dioxide because capture carbon. In here, you can clearly see the carbon footprint per kilogram of hydrogen. And again, methane pyrolysis quite solidly compete with SMR and probably far better than SMR, even SMR with CCS, very competitive. And you can see the comparison between solar PV, wind, nuclear, and then the biogas system. Biogas obviously has a net negative carbon emissions, so therefore it's much more healthier. But scale is a massive challenge for biogas. And coming back to methane pyrolysis, the good news is a number of companies and organizations around the world, in the US and Australia and Netherlands, Germany, Finland, and UK here, us scaling up methane pyrolysis technology, and has clear potential. Coming back to basic chemistry, SMR obviously is a chemical reactions, and then clearly see methane cracking and cracking methane for generate hydrogen and carbon, and then cost comparison here. Now, from here, how do we get this, for example, DOE target by 2030? And that's our journey. We currently looking at every single technology and see which technology has the maximum potential to reach this US DOE target. We haven't completed that study, and therefore I'm going to share our finding of our current studies with you. And hopefully in a couple of months, I will have a complete report coming out. So therefore, I'm going to focus on methane cracking. So we can see the methane cracking here. The two ways to reduce the cost of hydrogen methane cracking is add value for carbon. So if you can add value for your carbon and make products and so other products and other things, you can significantly reduce the cost of cracking and therefore cost of hydrogen. The other area is basically use waste heat instead of this energy, or at least offset some to reduce the cost of production. And the scale of carbon production here is that every single kilogram of hydrogen, you get 3 kilograms of carbon, solid carbon. If you take the cost of low-grade carbon today is about 0.4 to 1 US dollars per kilogram. And if you offset that from your hydrogen cost, assuming we find the applications, direct application of them without any further purification or processing steps, you can clearly see the benefit of to reduce hydrogen cost from current cost to lower the cost because of the gain from the carbon cost. And then if you can further add the value for carbon, you can clearly see you can clearly see that you could bring further cost down per kilogram. The cost of a special grade carbon here is about $2, and if you get $2, and you can clearly see here in the cost of hydrogen is in this space. Now, if you can further add value for carbon by basically processing it to a completely different level, and that where we can generate further technology and the jobs and economy, and clearly you are into the negative cost space. Whether we can do it as technologists, I think it's a clear demand for that to investigate this space. One of quite a few students, researchers in my group, including Joanna, who gave a nice talk yesterday in the energy storage session, looked at using the solid carbon that we make in supercapacitors, and she has done a very good study with some of our group people in here in Lefera to look at this space. And those who are not familiar, supercapacitors is a device that can store energy, and then various types of supercapacitors and hybrid and so on, and AA and so on. I'm not going into too much detail, but it can clearly provide energy storage solutions and a clear demand currently, and then demand could only increase. What Joanna has looked at is that loading carbon into supercapacitors and increasing the loading, and then see whether we can see any performance. What she has found is that she has compared making supercapacitor higher carbon loaded supercapacitors, and they compared that with industrial grade supercapacitors and then methane cracked to the byproduct supercapacitors. And clearly what she found in this study, which we submitted recently, is that supercapacitor made using the byproduct carbon from methane cracking outperformed the industrial grade carbon in high power, high mass loading capacitors. The high power, high mass loading capacitors are extremely important in electrical vehicle space and also many other stationary power space. And therefore, clearly, adding value for carbon, clearly strong argument there to use waste carbon from the methane cracking by hydrogen production. I can clearly see that the opportunity for bring down the cost. Now, the supercapacitor is not the only application of carbon. As I said earlier, there are many new applications as well. And these days we buy helmets, bicycles, and sports tools and things that comes with the carbon steel. So carbon is needed in that space. And we buy cosmetics, we buy soaps and toothpaste and things, we need carbon even. And people make submarine hulls and aircraft components with carbon. So the carbon is a really important commodity and going to, there's no doubt that's going to play a significant role. So there's an opportunity to methane cracking significantly to reduce the cost of hydrogen. So that's where we are in terms of our study. As I said, we are looking at other technologies as well in electrolysis, and then look at cost reduction potential at the same time looking at the carbon footprint. And I hope in a couple of months' time that study we'll be able to submit that study peer reviewing. And with that note, I'm going to, I hope I haven't taken, I hope I'm on target with and haven't taken the time much. And thank you so much for listening to this talk, and happy to take questions maybe later.
Upo, thank you very much. Right on target with time. I think we started a bit earlier as well, so perfect timing. That gives us a couple of minutes before moving on to the next talk. If anybody would like to ask questions, feel free to use the Q&A chat window or just the chat window as well to pose some questions. Anyway, we have one question so far from our audience, and I'll read it out in case people can't see it. It's from Felipe Mota Francisco, and he says, I think that CO2 carbon capture and storage in the decarbonization process is very important, as the use of renewable sources and environmentally friendly fuels such as hydrogen. What do you think about that? Do you expect that a better conjugation will happen soon? Okay, so if you'd like to comment on that question, Ugo.
Thanks, Killian. And Felipe, it's a fantastic question. And yeah, we spot on that. So my view is that the carbon footprint is something that we need to significantly focus on. It's not just about the energy related energy space, but any other space. For example, before I come to the answer, I'll tell you my view on that. So if you buy commodities like this or a sandwich, for example, if you buy a sandwich or a chocolate bar, we can see a number of calories, right? We can decide based on that whether we need this product or this sandwich or that sandwich or this bar or this chocolate bar or that chocolate bar based on that, along with our preferences. Tastes. I would like to see carbon footprint in each of those products. Even when I buy a pen, I would like to see what is a carbon footprint, total carbon footprint associated with production of this pen. So my view is that I think we could be super serious about this than that. So coming back to your question about it, yeah, carbon capture and storage is so important, and yeah, it is part of what I said, and it is really important that people have a quantitative an idea about the quantitative analysis about this. I think people need to work on more in this space. We have a lot of experts, and so that we can clearly relate. We should have tools to clearly relate our processes to understand the carbon footprint. Okay. Can I take the second one now directly, Killian? I can see the questions.
Good. Go ahead.
Oh, so, thanks.
I think maybe we should read the questions up because I'm not sure if the audience can see them.
Yeah.
So from Antonio Martinez, it's concerning hydrogen. What will be the main expected application? Heating, transportation, feedstock to produce other chemicals combined with carbon capture?
I think.
Go ahead.
I think all, to be honest. Now, I said that when we were running the company here in UK and in the US, we had a sister company in US as well for hydrogen solar. One of the real frustration about that is that time was that we had a really good team, and there were people who actually go around and then try to sell hydrogen. There was no one to buy hydrogen at that time, which is really sad and really surprising. Even around 2006, 2007. One of the reasons why that company had to wrap up at that time is there's no income stream, and we couldn't see any income stream coming in the near future. So you cannot survive a company if you do not. Okay, you can survive by doing R&D, but at least you should have a roadmap and predict that when you're going to make revenue. And we couldn't see that. And you were spot on that in your question, Antonio, that you really need significant application, not just about home heating. And in the UK, we are running trials in isolated, there's a couple of hundred. The Hype deploy phase two running by one of the gas providers called Cadent, looking at several hundred houses, and we'll basically isolate the system and then basically feed in blended gas and blended hydrogen. The idea is basically gradually move into 100% hydrogen for home heating. Transportation, obviously, we know that fuel cell and the direct combustion hydrogen are competing. Clearly, the fuel cell is a winner in terms of efficiency, but cost of fuel cell is a concern, and the fuel cell cost hasn't come down as much as we want it to be. But I think there are significant progress can be made. Feedstock, yes, I think traditionally, I mean, even now, the main application for hydrogen is the feedstocks and chemical sector.
Okay, thanks, Upal. We're just hitting time, but we'll have plenty of time at the end to ask other questions. Just a quick one. You showed a product which was a hydrogen-powered power bank. Somebody asked to know what the name of the product was. I guess
So
they
it
want to
is
look it up on Amazon and buy it.
Right. Now this is again a sad story that the company called Intelligent Energy started. Name of the product is UP, right? And they made about, from my understanding at least from those days, about 10,000 units of those. And they couldn't sell more than several hundred. And all
So
this.
you give them out as Christmas gifts.
Yeah, yeah. I mean, it's really sad because we got to phrase for the company to be brave enough to get into this and getting ahead of the game and then making the products but it wasn't going well, and for various reasons, and therefore, again, it is an unfortunate experiment, commercial experiment, quite significant commercial damage for the company, but they're doing all right and they somehow recovered from that. But that, I don't think you can buy it now, but it was on the market for a few years. And that's basically, since then the company has completely revamped, or they have reconfigured their business models. And I don't think they will look into this type of products anymore because they are looking at many different products at the moment. So Intelligent Energy is a company. I wouldn't want to just talk about them too much, but if you can search for Intelligent Energy, you can see the products and services they provide.
Okay. All right, Upal. Thank you. For those that pose questions, I promise to try to get back to them during the round table. So we're going to move on to our next speaker. Okay, so big thank you to Upal, and now I welcome Vanessa Gio. She's an arrayed senior researcher and head of R&D of the R&D department at the Argon Hydrogen Foundation in Spain. She's responsible for beginning novel and disruptive technologies from component research to full integration for addressing proof of concepts, technology readiness level 3, and validate at pilot scale and relevant environment, which is technology readiness level 5. She's a chemist and holds a PhD in material science. She graduated in 2006 from the Autonomous University of Madrid in the field of new materials for Syria-based solid oxide fuel cells. She has over 15 years of international experience in developing novel materials and advanced devices for energy conversion and storage technologies related with hydrogen and other renewable gases. Interesting term, that one. She works globally to connect all key players within the value chain, from the scientific community to industrial partners. She has deep competences in high-temperature fuel cells electrolyzers, low-temperature water electrolyzers, and dense ceramic membranes. As a scientist with strong expertise in ceramic processing and material development, she's increasingly working on demo projects and the integration of renewable energies. So I welcome her talk, which is the production and use of hydrogen as a decarbonization tool. Vanessa, welcome, and the floor is yours.
Thank you so much for the kind introduction. And I'm very happy to be here today to share with you my experience on the field. So I will try to share my screen now. Let's see if it works. Okay. I hope that you can see my screen, right?
Yes, we can.
Yes, thank you. So yes, as I was presented, I am a senior researcher at the Argon Hydrogen Foundation in Spain, where also I am in charge of develop or being responsible of all the research and innovation lines or activities in this institution. So let me introduce first what is the meaning for this RID institution. In fact, RID is just a program from the region of Aragon in Spain, in the northeast of Spain, and it's an agency that it was created in the 2005 by the government of Aragon. And the idea was to try to promote research, development, and innovation in different research lines or technology tracks, and try to attract people from abroad just to Spain. So basically, the idea was to hire experienced researchers and well-established researchers in different lines, from the biomedical sector up to the energy sector, like in my case, that were abroad for at least 6 years. In my case, it was a little bit more, because I was mainly in Scandinavian countries, in Norway and Denmark, during 8 years. So the idea is just to going back to the country and try to implement a good research. So in this way, this is how I end up in my hometown, in fact, because I was born here, and I decided that my host institution would be the Alkaline Foundation. So why Alkaline Foundation? Well, this institution is a private, non-profit research entity created to promote the use of hydrogen as an energy vector. So it was completely aligned to my research or my experience. And also the reason because I decided this institution is because it's quite close, I would say, to the industry. And since all my career, of course, I was developing my scientific career in universities, research centers, but always with quite applied focus. I was, since the beginning, quite close to the industry. And here in Spain, I found that this entity was doing something similar, but in my country. And this is why I decided, yes, this institution. Aragon Foundation was also promoted by the government of Aragon in 2003 with the support of all the sectors or industrial sectors at the region. So in this way, our board is compiled by 78 members. Right now, we have companies from the energy up to the motor sector, also chemistry, so all kind of industry that is related to hydrogen or with renewable, let's say, fuels or alternative fuels, but mainly an interest in hydrogen. So the institution, yes, here I just wanted to share with you just some pictures about the institution. So we are quite small, I would say. We are only, let's say, 30 people in the institution, but we are quite active and quite active at, I would say, international level. So we have mainly a lot of international projects from the European Union calls, also some others at different levels. I will let you know later. But right now, I would say we have more or less around 20 projects, running projects, ongoing projects. Our institution is kind of kind of, let's say, pioneer and even unique to work with large scale hydrogen equipment. So we have big cylinders with all the ATEX and all the safety measurements and detectors and components to work with pure hydrogen and with large scale equipments, I would say. We have, of course, renewable energy. We have some wind, some PV, solar panels, also of grid. So here on the right, this picture on the top right, here you can see some solar panels and also this white box in the front of the picture. This is an electrolyzer with a specific technology that produced a hydrogen from the solar panels, and is like we are here, or it was a European project that we were replicating producing hydrogen in an off-grid. So meaning directly from the solar panels and not connected to the grid. Yeah. Also, of course, we have test benches. So meaning we have test bench for testing alkaline technology. So meaning water electrolyzers based on alkaline technology. Also, we have, as I said, electrolyzers based on the polymeric exchange membranes, a different technology. And we are expecting soon to have also anion exchange membrane test bench. We have also right now an electrolyzer based on the anion exchange membrane that is producing the green hydrogen, so it's linked to renewable energy. And yeah, we have also equipment or components for hydrogen storage, of course. We have a hydrogen refueling station. And yes, and let's say the last, or the, yes, I would say the last baby of our institution is this testing loop on the right, on the bottom. This test loop is replicating the pipeline system that you can find at a transmission level, so at high pressure. So meaning we are replicating a gas grid, high pressure, and we test how different blends of hydrogen methane behave. I will come to this later. So yes, let me continue. Yes, let's see, well, it's not, yes, now. So we are quite active, as I said, at European level. So we are members of this Hydrogen Europe. We are both members of the Hydrogen Valleys pillar. Also, of course, we are active at the International Energy Agency, different committees and working groups, CENELEC, yeah, and different environments, let's say. And also, I am one of the let's say, leaders or roadmap leaders trying to develop a roadmap for hydrogen production from electrolysis at the European Union. Yeah. So yes. Yeah. So what is our motivation? Well, our motivation, of course, is try to find a safe, reliable, economical, and sustainable energy backbone system, of course, and why not based on hydrogen? The main challenges were already well discussed. So we are facing this climate change, and the fossil fuels resources are limited. And of course, we have more and more this demand for the energy. So we should find a solution, of course. And the question now is, will hydrogen be this one of the actors of this of the skeleton key to unlock a carbon neutral world. And I would say, yes, why not? In fact, could be one of these main players. The reasons are multiple, as the previous talk just also highlighted. Hydrogen allows, for example, linking key vectors or key sectors, sorry. We have, of course, the power grid, the gas grid, and we can find this interconnection. Also, is the main contributor to allow wider penetration of renewable sources, provides large-scale storage options, of course, and finally can also absorb, of course, the excess of renewable electricity production and provide flexibility to the electricity grid. So these are some of the main reasons for why we are pursuing these hydrogen-related technologies. I wanted just to make a summary here about how can we produce this hydrogen, green hydrogen. Of course, we have water electrolysis. I just put here the three main technologies. I would say the more developed, proton exchange membrane, anion exchange membrane. I will not go into details, or alkaline. The two more developed, of course, are PEM and alkaline. And anion exchange membrane is also getting into or is coming to play a role also, I would say. Of course, we also have high temperature technologies based on solid oxide materials, also proton conducting ceramic materials. And in this case, we call it steam water electrolysis, since, as I said, this is high temperature, meaning above, we could say, 700 degrees, for example, Celsius degrees. Water electrolysis, we could call it, for those technologies, up to 150, just to provide you the picture. Then we have other concepts. Of course, we have other routes like photocatalysis, photoelectrocatalysis, our biomass reforming, solar thermochemical, and some more. And then, of course, we have also novel concepts and operation modes, I would say. For example, we can find new modes as co-electrolysis, or the use of the produced hydrogen from non-pure water, for example, or even technologies that are reversible. So meaning that we can produce hydrogen as an electrolyzer, but at some point, the same technology could be used as a fuel cell. So meaning that since when the hydrogen is fed to the technology, we could get energy and heat from energy and heat if it's high temperature, or just energy if it's low temperature. But we are both modes, so electrolyzer and also fuel cell in the same device. Yes. So I wanted to highlight here just a few lines about some technologies that I think that are important to highlight. For example, we have this green hydrogen production by alkaline water electrolysis. We developed on the frame of this project. It was a European project that finalized in 2019. I was the main coordinator of this project, and the idea was try to develop a new or an advanced electrolyzer that could be able to operate in dynamic operation, on dynamic mode. Why? Is because at the time when you want to correlate these kind of technologies with renewable energy or with renewable sources, sometimes it's also good, or you can get a profit if those technologies are not only adapt to the demand or to the need of the energy, so meaning that at the time when it's needed to absorb energy, you can produce, or you can just reduce the load or whatever, but also could provide grid balance. So the idea was to develop a new concept based on the Alkaline, because it was the most developed at that time, and try to see if it was possible to adapt the new stack to this mode. The point is that the materials, from the materials point of view and from the components point of view, is not the same when you operate in a nominal conditions than that in dynamic conditions. Basically, it's very important to develop novel membranes, but also novel electrodes, of course, that could allow this high dynamic operation and in a broad range of carbon density and so on. So in the frame of this project, we design, develop, and implement balance of plant, of course, and test benches for high dynamic operation. And we carry out some accelerated stress tests also to these stacks for the specific application of the project. Here I just wanted to present a brief summary of what we did. So some electrodes were developed, membranes, all together were put in a stack that the manufacturer just assembled. This stack was tested at our facilities. It was a 10 kilowatts stack. It was tested in this pre-pilot scale test bench that we call it. And then after the first screening of those most promising materials assembled in the stack, we go to the next step, that is at industrial scale. Also is a test bench at my institution. And here we develop, or we demonstrate at a relevant environment the stack with these dynamic profiles. I will not go into detail, just to show you that we could arrange some dynamic profiles. We could get the efficiency of the stack, the final efficiency, that it was a key performance indicator of the project. Also, we developed novel electrodes, not we, but the consortium, of course, developed novel electrodes with a broad range of application regarding the carbon density that in fact were quite promising, I would say. And also we perform some dynamic profiles, also aligned to another project that also we were participating. This project is called the QualiGrids project, also an international project from the European Union. In this case, this project just developed, let's say, a testing protocols for pre-qualification of the electrolyzers to provide grid balancing, and in base of those protocols, I would say, we took these protocols and we applied to our project, an integration project. So the industrial scale, the big one that you guys see before, we developed these dynamic profiles. Then we came to the second line, this is storage, transport, and distribution. In this case, I will just go very quickly. We have different areas, and one of the areas that is important to us is the hydrogen transport by the gas grid. Why? We have a lot of reasons, but one of the main reasons that I would say that is important, why it's important to investigate this hydrogen injection, is because it's also possible not only to transport the hydrogen through the gas grid, but also is a way to decarbonize the gas grid. Okay. Yes. So here I present just very briefly this project. It's a project that is running right now. I am the coordinator of the project, and the idea is try to to test and to validate different, or not to validate, but it's just to investigate, let's say, the effect of different admixtures, hydrogen plus methane, plus also some impurities, and try to inject this in this testing loop at high pressure. So we go up to 80 bars and try to see how is the effect of the blend, not only in the material pipelines. So we have previously developed a survey about which are the materials more frequent at European level in the gas grid. So we have identified those steels, let's say, but also in the components of the gas grid, the most important components on the gas grid. So we have detected like the compressor, regulator pressure, filter, and all these components also are tested at this blend. Yeah, I will just skip this, I think. So right now we are testing 10-20% in volume of hydrogen in methane. And the preliminary results are that there is no significant change, let's say, in the gas composition, meaning that the components that we have right now would be okay for this blend. Of course, this is only in the components. We should wait until the first testing campaign finished to characterize the materials of the pipelines. And finally, I wanted to bring here this nice project. This is an international project called Volumetric. It's in international cooperation with Japan. So it's not only the European Union involved in the project, but also is Japan and also is Brazil involved. And the idea for this project is to try to produce liquid fuels from CO2 and hydrogen. And which kind of liquid fuels? Well, the idea is to try to synthesize sustainable jet fuel, so for the aviation sector. I think that I will just finish with this slide. You are very welcome to enter into the website. This is a project that also I'm the coordinator of the project, and that the validation of the cascade reactor will be done at our facilities. And yes, and the idea is just, of course, to produce this jet fuel at mild conditions and at one step. So just to provide an alternative route to Fischer-Tropsch synthesis. And thank you so much. And please, if you have any question, yes.
Thank you, Vanessa. Great. Very interesting talk. We have 1 minute for questions to keep to the timetable for the next speaker. But we have one question from Antonio Martins, which maybe you could try to answer, which is the selection of the material. Was the selection of the materials taken into account regarding their environmental impact? One of the problems of current electrolyzers is the use or utilization of rare and noble metals in the electrolyzers. That increases their cost and also an environmental impact. So mining, et cetera, et cetera.
Yes, in fact, I invite you to visit the website. We have also uploaded public deliverables. And I would say that I think that there is one deliverable regarding life cycle assessment. In this case, it was a study, but also since we were considering alkaline technology, from this point of view, is more convenient than other technologies. But yes, we consider this.
Okay, all right, thank you. Very well, thank you, Vanessa. If I could ask you to stop sharing your screen.
Yes.
Fantastic,
Sure.
Thank you. And I'll share my screen to introduce our next speaker. And this is brilliant, we're keeping on time. Very well. It is my pleasure to welcome and introduce Lifeng Liu from the Iberian National or Nanotechnology Laboratory in Braga. He is currently a group leader in nanomaterials for energy storage and conversion. His group has been working on the development of new nanostructured materials and their applications in electrochemicals, energy storage and conversion, including water splitting, solar fuel production, rechargeable batteries, and supercapacitors. He has a PhD degree in condensed matter physics from the Chinese Academy of Sciences and did his postdoctoral work at the Max Planck Institute of Microstructure Physics between 2007 and 2009. Before joining the INL in 2011, he was a staff scientist and group leader at the Max Planck Institute of Microstructure Physics. He was recipient of an FCT investigator grant in 2014, the Young Researcher Award 2015 by the Portuguese Electrochemical Society, the Scientist Medal 2018 by the International Association of Advanced Materials, the IAAM, and the Emerging Investigator 2019, elected by the Royal Society of Chemistry journal Chemical Communications. The title of his talk for today is High Performance Catalysis and Advanced Cell Design for Hydrogen Production via Low Temperature Water Electrolysis. Lifeng, the floor is yours and welcome.
Okay, thank you so much, Killian, for your nice introduction. Let me try to share my screen. Okay, great. So good afternoon, everyone. First of all, I would like to thank the UT Austin Portugal Program for the kind invitation. And it's a great pleasure to be here today to share with colleagues from academia and industry, both the University of Texas and the Portugal side, our recent efforts to developing advanced high performance electrocatalysts and advanced cell design that can be used in PM and alkaline water electrolyzers for hydrogen production. Firstly, I'll speak why hydrogen and water electrolysis are important to our future energy supply and why high performance, low cost, sustainable catalysts are critically needed. And then I will give you some examples showing the efforts we've made in the last few years to improving the water electrolysis performance while developing efficient and stable electrocatalysts for hydrogen and oxygen evolution reactions, as well as advanced cell design. So in the end, I will briefly summarize my talk and give you some perspectives. Well, so why is hydrogen important and why is water electrolysis a promising approach to hydrogen production? So previous speakers already gave a very comprehensive overview about this, and I will just try to be brief. So presently, 137 countries in the world have pledged to achieve carbon neutral goals in the middle of this century. So for instance, the world's largest emitter, China, announced last year a timeline of 2060 to reach carbon neutrality. And US, Europe, and many other countries, as marked in the light blue in this chart, are committed to reaching carbon neutrality by 2050. Well, as mentioned previously, hydrogen actually has a high energy density and carbon-free energy carrier will be a key enabler for decarbonization, helping to reach the carbon neutral goal. To do so, hydrogen must be produced in a sustainable and green manner. For instance, through water electrolysis in combination with renewable sources. So renewable hydrogen will be an important vector of decarbonizing not only the transport sector and power sector, but also the hard-to-abate industries such as metal refining and ammonia production, as illustrated in this graph. Well, there are several major means for mass production of hydrogen, including thermochemical, electrolytic, direct solar water splitting, and biological approaches. Thermochemical means only produces green and blue hydrogen, which is not preferable, obviously. But the other three approaches allow for green hydrogen production, but currently direct solar water splitting is still not technologically mature and is only expected to be introduced in the market massively by 2050 also. And therefore, water electrolysis and biological hydrogen production, in particular water electrolysis, have been chosen by the European Commission as viable and potentially economically competitive approach for large-scale production of hydrogen. Accordingly, the Commission also launched a green hydrogen initiative last year, aiming to install 40 gigawatt electrolyzers for green hydrogen production in Europe by 2030, and another 40 gigawatts in associated countries in the European economic areas. So now let's see why high-performance electrocatalysts are critically important to fulfill the ambitions for large-scale electrolyzer installation. So what I'm showing here is an illustration showing the structure of a typical membrane-based water electrolyzer cell. So the membrane, either proton exchange or anion exchange, serves as a polymer electrolyte and is coated with hydrogen evolution catalyst on the one hand, and on the one side, and the oxygen evolution catalyst on the other side. So the catalyst-coated membrane is then sandwiched by gas diffusion layers and bipolar plates, forming a single unit that can be assembled together with other units into stacks and modules. Well, electrocatalysis is one of the most important components of the electrolyzer. It's essentially determining the hydrogen production performance. For small-scale electrolyzer below 1 megawatts, the catalyst cost typically only accounts for, let's say, 5% of the system cost. However, the cost pattern will dramatically change when the capacity of electrolyzers goes beyond megawatts to gigawatts. In this case, the catalyst cost will become a major cost contributor, given the markedly reduced balance of plant cost, especially if we consider that we are going to deploy water electrolyzers from the current global capacity of less than 0.2 gigawatts to 6 gigawatts by 2024, and 40 gigawatts by 2030. No, this is only the European scenario, and then the need for electrocatalysts will be huge in the coming years. It's worth mentioning that many electrocatalysts currently being used, as already mentioned in some of the participants, they constitute critical raw materials, typically platinum group metals, the supply of which is vulnerable to Europe. So, for example, iridium is an indispensable oxygen evolution catalyst used in PM electrolysis. According to a recent economic analysis, so if we want to take advantage of PM electrolysis technology for hydrogen production, we must endeavor to reduce iridium utilization without compromising catalytic performance, and on the other hand, recycle iridium with a high rate over 90%. Otherwise, the supply of iridium will be unable to meet the global demand. I don't have time to go into details, but I would like to suggest you, especially those from industries, read this paper through, and it's actually a very interesting and important analysis. And this highlights how important it is to make innovation in catalyst design and synthesis. So in the following, I will show you what we have been working in the last few years on new catalyst development to improve water electrolysis performance. So given the time limitation, I will not go into details for each example I'm giving, but I will give you the references. And or if you are interested, you can also contact me directly via email later on. So let's first see the PEM electrolysis catalyst. So PEM electrolysis typically operates in an acidic environment, and therefore, aside from high activity, acid stability is crucial for HER and OER catalysts. Platinum group metals, including platinum, iridium, and ruthenium, typically must be used in industrial PEM electrolyzers. So from the cost and sustainability perspective, as I mentioned before, PEM should be as little as possible in this catalyst. Of course, it would be brilliant if we are able to completely substitute PGM with inexpensive earth-abundant metals. And there are many R&D in the laboratory along this line, in particular for PGM-free HR catalysts, as I will mention later on. However, iridium is by far still indispensable for use to catalyze the oxygen evolution reaction in PEM electrolyzers. So therefore, it's important to largely reduce the utilization of iridium while keeping good OER performance. Reducing catalyst size is an effective strategy to this end. So recently, we have developed a simple impregnation post-annealing method that allows us to deposit ultra-fine iridium oxide clusters with an average size of about 2 nanometers on high surface area hydrothermally treated porous titanium foam, as you can see here. So these iridium oxide clusters are oxygen deficient, and our experimental studies and DFT calculations and demonstrated that such oxygen deficiency is able to enhance the oxygen evolution activity by lowering the energy barrier of the rate determining step of the OER process. So as a result, these ultrafine clusters show the high specific activity, proving that they are intrinsically active, and more importantly, they show a mass activity of around 200 amperes per gram of iridium at an over potential of 300 millivolts. And mass activity here is actually a metric obtained by normalizing the catalytic current by the catalyst mass, which reflects the effective utilization of precious metals in the catalyst. And to more comprehensively assess OER performance, we further draw a plot of mass activity versus the apparent activity, namely the over potential needed for the catalyst at a given geometrical current density. For practical applications, the catalyst should preferably have both high mass and apparent activities, namely positioned in the upper right corner of this plot. As you can see, this is indeed the case for our catalyst. And it's worth noting that in many publications, the mass activity is usually overemphasized. In particular, for the single atom catalyst developed recently, it's very easy to have a large mass activity given their very low loading mass density. However, this is only, I would say, a mathematical trick. So in practical, what it actually is, we need to reach a given current and therefore have to increase the thickness of catalyst layer, which will hinder mass and electron transfer in this case, compromising the overall performance of the electrodes. And therefore, we would strongly recommend to consider both the performance indicators to have a just assessment. Well, another example is the ultrafine iridium ruthenium clusters supported on telluride nanoparticles, which we prepared in a one-part solar thermosynthesis process. And the catalyst can reach a mass activity of 1046 ampere per gram of iridium at the over potential 300 millivolts, and meanwhile show a good apparent catalytic activity, as you can see from this graph. And the enhanced performance is ascribed to, on the one hand, introduction of ruthenium, which is more catalytically active than iridium, as well as the ultrafine cluster size, which allow more active size to be exposed. On the other hand, to also the strong electronic coupling between the iridium ruthenium clusters and the tellurium nanoparticle support. So we have experimentally observed the banding energy shift of our catalyst with respect to the control samples, and we explained this phenomena based on DFT calculations. So in addition, by loading iridium ruthenium clusters on a metal organic framework derived carbon support, we further increased the mass activity to 2041 amperes per gram at a lower potential of 300 millivolts. But I will not go into details about this work. So besides OER catalysts, we also managed to develop a hydrogen evolution catalyst, for instance, atomically dispersed ruthenium and iridium. So this is a high resolution TM micrograph where each broad spot you can see here corresponds to one ruthenium atom. And this kind of catalysts enable maximal utilization of metal species, and every noble metal atoms can be efficiently used. So not surprisingly, the catalyst can achieve a high mass activity of 25 ampere milligram of metal, and at the over potential of 100 millivolts, and deliver also a high turnover frequency of 13 per second. Well, as I mentioned before, there are some non-PGM catalysts that have exhibited reasonably good catalytic performance for hydrogen evolution in acidic solution, which can potentially replace platinum in PM electrolyzers. So to this end, we have been working on transition metal phosphide and sulfide-based catalysts. In particular, metal phosphides show a substantial promise because of their favorable electronic structure, high electrical conductivity, and good acid stability. So for example, we developed an easy approach to the fabrication of self-supported nickel phosphide nanosheet electrodes, just by a chemical reaction between a commercially available porous nickel foam and the red phosphorus vapor at an elevated temperature for a short time. So these electrodes show the HER activity favorably comparable to the commercial platinum carbon benchmark, and good catalytic stability, as you can see here, from the coronal potentiometric curve, and also the post-mortem SAM and EDX analysis. So now I'm going to show you some transition metal-based catalysts for use in alkaline or anion exchange membrane, namely AEM analysis, electrolysis. Well, typically, we manage to electrodeposit metallic nickel on the surface of carbon paper, which can be used as a gas diffusion layer or a porous transport layer, which was then subject to phosphorylation, converting metallic nickel into nickel phosphide nanosheets, as you can see in this graph. Interestingly, we demonstrated that the electrode can efficiently catalyze both hydrogen and oxygen evolution reactions, showing bifunctionality. In this way, we may simplify the fabrication of electrolyzer cells. We have comprehensively investigated the oxygen evolution performance of nickel phosphide and found that nickel phosphide was subjected to morphology, crystal structure, and composition transformation under the OER conditions, forming a nickel oxyhydroxide that is more active than the nickel hydroxide directly grown on the carbon paper. Moreover, we found that bimetallic cobalt nickel phosphide showed HER and OER catalytic performance better than the monometallic cobalt phosphide and nickel phosphide. And the self-supported cobalt nickel phosphide nanowire electrode can catalyze alkaline and water electrolysis at 100 milliampere per square centimeter for more than 3,000 hours without significant degradation, as you can see in this graph. But we also studied how the number of transition metal species and their different combinations affect the oxygen evolution performance in alkaline solution, and we observed a clear trend in the OER activity, showing that introducing additional transition metal species enhances the OER activity by changing the electronic structure of the catalyst. Besides, we also did many other works along this line, which I don't think I have time to go into details today. So if you are interested, you are welcome to read papers that we published on this topic. And there's one more example I would like to show you about the alkaline electrolysis, which is that using porous phosphide form as bifunctional electrodes, we have recently demonstrated alkaline electrolysis at a high current density of 1 ampere square centimeter at about 2 volts with an outstanding long-term stability of 4,000 hours. Okay, let me just talk a little bit about the cell design. So note the cell design I'm saying here does not mean a specific design, for instance, in cell geometry, size, flow channel, so on and so forth. Instead, the focus is placed mainly on the cell configuration with the aim to save the energy input into electrolyzers. So I'll give you some examples in the following so that you will have a better idea about what I mean here. Well, firstly, I will show you how bipolar membrane can help reduce the electrical energy needed for water electrolysis. A bipolar membrane consists typically a cation exchange membrane from selective to cations joining with anion exchange membrane from selective to anions. And there's a built-in electrical field. So pointing from the AEM to CEM, as you can see here, and depending how the bipolar membrane is positioned with respect to the anode and the cathode, and there are 2 configurations, namely the reverse bias configuration and the forward bias configuration. In the reverse bias configuration, the built-in electric field will dissociate water at the AEM, CEM interface, and the resulting hydroxy ions and protons will move to the anodic and cathodic compartments respectively, maintaining the pH gradient between the 2 compartments. In this case, the operation of bipolar membrane electrolysis is pretty similar to PEM or of AEM electrolysis. However, in the forward bias configuration, where CEM faces to the anode and AEM is facing to the cathode, the electrochemical neutralization will happen at the interface here, so which can help reduce the external electrical energy input for driving water electrolysis. Another advantage of bipolar membrane is that the OER and HER can take place in kinetically favorable conditions for each reaction, namely OER in an alkaline condition and HER in the acidic condition. Moreover, given the fact that, as I mentioned before, non-PGM HER catalysts that are active and stable in acid are available, and there's in principle no need use any PGM catalyst in bipolar membrane electrolysis, as I will show you in the following slide. So in a recent work we published, we used a bifunctional self-supported cobalt-nickel phosphide nanowire electrodes as the anode and cathode. In a single cell electrolyzer, we have demonstrated that bipolar membrane water electrolysis can occur at a voltage as low as just 0.8 volt. And a current density of 100 milliampere per square centimeter can be reached at about 1.06 volts in the forward bias configuration, of course. And the voltage gap is similar to the magnitude of the electrochemical neutralization induced potential difference, confirming that neutralization between the hydroxy ions and protons play an important role here. Moreover, the cell can operate stably for at least 25 hours, as you can see from this graph. Well, to further demonstrate the advantage of bipolar membrane electrolysis, we connected the cell with commercial solar panel. As you can see here, upon light irradiation, the solar panel generates an output voltage of only 0.9 volts, which is normally not enough to enable water electrolysis, because this is well below the thermodynamic potential of water splitting, namely 1.23 volt. However, if a bipolar membrane is used in the forward bias configuration, a catalytic current density of 13 milliampere per square centimeter can be generated, and accordingly we can clearly see the evolution of hydrogen and oxygen gas bubbles on the electrode surface as shown here. Okay, the last example I would like to show you is to reduce the actional energy improved by replacing the oxygen evolution reaction with a less energy demanding reaction, such as electrooxidation of small molecules. As you know, the oxygen evolution reaction involves 4 successive proton coupled electron transfer steps, and is both thermodynamically and kinetically demanding. So the theoretical minimum on-site potential of OER is 1.23 volt versus reversible hydrogen electrode. But in reality, a lower potential at least 100 or 300 millivolts will be needed, even if the most active catalyst is used. So if we can replace OER with, for instance, hydrogen oxidation reaction, which can take place easily as a much more negative potential, we can accomplish hydrogen evolution at the inode of the electrolyzer cells, and in the meantime, remarkably reduce the electrical energy needed, given the anodic reaction now becomes significantly less energy demanding. Moreover, the negative shift of anodic reaction potentials may open other possibilities. For example, avoiding the interfering reaction from happening, as I will show you later. Well, having this in mind, we recently demonstrated that the coupling of the hydrogen evolution reaction with the hydrogen oxidation reaction using bifunctional cobalt and nickel phosphide nanowire electrodes as anode and cathodes, we show this will open a great opportunity for direct alkaline seawater electrolysis. So direct seawater electrolysis is a very promising approach to green hydrogen production, because we can take full advantage of offshore solar and wind energy and to power electrolysis and eliminate the need for high purity water. So, however, one of the long-standing technical challenges is the interfering chlorine evolution reaction taking place above 1.73 volt versus RT. So by adding just 2.1 molar hydrogen in an alkali seawater electrolyte, we found that the IV curve of electrolysis is significantly negatively shifted, and we are able to reach a high current density of 500 milliampere per square centimeter at a voltage of only 0.53 volt, far away from the on-site of chlorine evolution. Well, since I have run out of my time, I will not get into details. Well, to summarize, in this presentation, I've showed you our recent efforts to making high-performance electrocatalysts and exploring new cell designs for use in low-temperature water electrolysis. So from catalyst perspective, for PM electrolysis, if we want to take its advantage and increase its penetration in the market, then we will have to further reduce the usage of PDM in electrolyzers. Alternatively, it's certainly preferable to use PGM-free catalysts in PM electrolyzers, but this is very challenging, and more research and development will be required. For alkaline electrolysis, we will continue to develop new catalysts with improved performance, and meanwhile consider the sustainability when designing the catalyst. The cobalt phosphide form that I showed you previously is perhaps not a good choice, because cobalt is actually a critical raw material that we should avoid using in electrolyzers. Moreover, we do believe that seawater electrolysis holds great promise for green hydrogen production, and we will further tackle the technical challenges in our future research. In terms of cell design, the availability of bipolar membrane electrolysis are high current densities for longer durations has not yet been has yet been validated, and we believe coupling hydrogen reaction with electrochemical synthesis of fuels or chemicals will bring more added values, which deserve, of course, further investigation. So, of course, and there are these are only considerations from Catalysis, as I said before, and the cell design standpoints. So we are definitely willing to collaborate with partners working at a higher TRL to help us validate the catalysts that we develop in stacks or modules, and also with the catalysts and component suppliers to explore the scale up of our catalysts and the electrodes. In this way, we hope that we can contribute to the European Commission's ambition toward green hydrogen deployment. So finally, I thank you all for your attention, and if you have any questions, I will be happy to answer them. Thank you.
Yifeng, thank you very much for that very informative talk. Very detailed, but very broad. Lots of information there, lots to think about. We're running behind in time, so I'm going to leave your questions for the roundtable session.
For that. Yeah.
No problem. So if you could stop sharing your screen so I can present our next speaker. Great. So it is my pleasure to welcome Claudio Pistida. He was a speaker here on Monday when we were talking about the Green Deal or social aspects required that need to be overcome. But today he'll be talking on another subject. He's very interested in several different aspects of material chemistry, chemistry of micro and nanostructured materials with an emphasis on hydrogen and metal hydrides, complex metal hydrides, and reactive hydride composites. Tuning of multi-component hydride systems, both kinetic and thermodynamic, also material synthesis using high-energy ball milling devices, and research and development of high-performance, low-cost hydrogen storage systems made from recycled industrial waste, metal waste. And as I said, his talk on Monday was as a European Climate Pact ambassador from the European Commission, and his thematic areas here are climate education awareness raising, energy, and sustainable transport. His talk today will be on nanostructuring metal hydride-based systems for hydrogen storage. Claudio, welcome, and the floor is yours.
Thank you, Killian, for the nice introduction, and you are the only one that can pronounce my family name perfectly, actually, so thank you very much. So, good afternoon, everyone. So once more, I'm Claudio Pistida. I come from the Department of Material Design in the Institute of Hydrogen Technology at the Helmut Zentrum Iron in Germany. So can you see my screen?
Yes.
Yes, we can.
Perfect, good. So as Killian said, we will speak about nanostructuring metal hydride-based system for hydrogen storage. So a brief outline of this presentation. So I will speak briefly about hydrogen economy. Has been already said everything in the previous presentation from Upul, Vanessa, and Yifeng. Then we will speak about how hydrogen can be stored, so physical method or chemical method. So we will speak about metal hydride. We will see what are the issues, some of the engineering issues associated to the use of metal hydride as a hydrogen storage system. And then we will speak about the possibility of destabilizing metal hydride-based system through different methods. Then we will try to summarize the main idea of this presentation in the conclusive session. Okay. Now, toward an hydrogen economy. So the fact that hydrogen it's really useful for decarbonizing our society has been previously mentioned in the other presentation. Now it's clear that hydrogen has to be synthesized using renewable energy sources to be really effective in decarbonizing our society, because then it can be used like Yifeng, Vanessa, and Upul mentioned in the several sectors like transportation, but our power sector and the manufacturing sector. No, the idea of using hydrogen as an energy vector is not new. If we think that already was mentioned in the Mysterious Island from Jules Verne in 1874. So that it's something that is quite anew, let's say, as an idea. Now, hydrogen, if we look at the periodic table of the element, we see that hydrogen is located in the upper left corner. What does it mean? That means that it's the simplest element of periodic table, but is also the lightest. And to be the lightest has some implication. Now, if we consider hydrogen in his bimolecular form, hydrogen is relatively not dense as a material. So as a density, a gravimetric density that is only 0.83 gram per liter. These are at ambient conditions, so 1 bar and 20 degrees C. Now, if we want to store energy in hydrogen, it's important to try to put as much as possible as hydrogen in a fixed volume. So therefore, what is normally done to increase the energy density of hydrogen is to compress it. No, so one of the most easiest way to compress hydrogen is the one at 350 bar. Now, when we compress the hydrogen at 350 bar, we see that the gravimetric hydrogen capacity increases from 0.83 gram per liter to 23 gram per liter. If then we compress it even further from 350 to 700 bar, the density, gravimetric density, increase up to 38 gram per liter. And then if we want even to go further, there is another possibility. So to liquefy hydrogen at cryogenic temperature. So we are speaking about minus 252 degrees C. And in that case, what we obtain is we can have a gravimetric hydrogen capacity of 71 gram per liter. Now, let's consider we want to store 5.6 kilogram of hydrogen. 5.6 kilogram of hydrogen is what is needed for a fuel cell car to run roughly about 600 kilometers. So if we would use uncompressed gas, so at ambient pressure, we will need for 5.6 kilogram, roughly about 6,750 liters, so way bigger than your car. Then, but if we compress the gas to 350 bar, we will need only a tank that is 243 liter big. That is still huge compared with the dimension of your car. If you increase it to 700 bar, that is what you can find in Toyota Mirai, for example. 750 is the Toyota Mirai. You need a tank, only the tank, something like 150 liter. And if your car will host a liquid hydrogen tank, you will need just 78 liter for the tank. Fine. So you see how important it is to find a way to minimize the space that our hydrogen occupies to really effectively use it. No? So now hydrogen, we say, is not dense. So if we look at this graph here that shows the volumetric energy density of some of the most common fossil fuels, you will see that hydrogen, although in a pressurized form, has an energy density that is much smaller than the most common fossil fuels like methane, methanol, propane, gasoline, or diesel. And even if we liquefy, this value remains smaller. Now, we know that many metals and metalloids have a strong affinity for hydrogen. So once hydrogen gets in contact with these metal and metalloids under the proper pressure and temperature condition, the bond between hydrogen and hydrogen is split, and the atom of hydrogen react with the metal or metalloids, forming the so-called metal hydride. Here we have depicting a reaction of the formation of metal hydride. And you can see that normally, if this reaction is energetically favored, it will be accompanied by the release of a certain amount of heat. Now, so the reaction is exothermic. And this is important later for application. Now, metal and metalloids, here you see the periodic table of the elements. And as you can see, these are all the metal and metalloids that may form metal hydride species. Again, the formation of metal hydride is not anything new, as it was already reported by Graham in 1869. And what he discovered was that palladium could reversibly exchange or store hydrogen. Good. But why I spoke about storing hydrogen metal hydride? Well, before we say that it's important to store the maximum amount of hydrogen in the least volume. No, so what we saw is that we could store hydrogen up to 71 gram per liter of volume in liquefied form, and that was using physical method to store hydrogen the maximum. No, however, when you use a metal hydride, you can reach up to 150 gram per liter, so practically more than the double than in the liquefied hydrogen. So that is the reason why metal hydride are so interesting for storing hydrogen. Now, there are some issues. So we say that metal and metalloid have a strong affinity for hydrogen. No, the problem is that the strong chemical bond that they form, then it's the cause for releasing hydrogen later only at high temperatures that often are well above the 100 degrees C that a PM fuel cell will require as a maximum temperature for operating. No? So this high temperature and these strong bonds lead to slow diffusion of hydrogen in the hydride in and out. So your kinetic of hydrogenation, the hydrogenation is sluggish. And moreover, the amount of hydrogen, of heat that is released during absorption or desorption is an engineering issue, because this amount of heat has to be something that can be provided in the best case from the exhaust heat of the PM fuel cell that you are using. And moreover, we have to consider that the more the heat that has to be exchanged, the more sophisticated has to be the heat management. Keeping to mind that the heat conductivity of metal hydride is extremely poor. Metal hydride are practically considered as a thermal insulator. Now, one of the hydride that historically has been studied the most for hydrogen storage purpose is magnesium hydride. Magnesium hydride, the first study about hydrogen storage in metal and magnesium hydride was reported in 1951 by Egon and Wiberg et al. Now, magnesium, we know that react at certain temperature with hydrogen to form magnesium hydride. Really important, the magnesium hydride has a high gravimetric hydrogen storage capacity, 7.6 weight%, and the volumetric hydrogen capacity of 110 gram per liter. Remember that in liquefied form, hydrogen had something like 70. Now, the reaction enthalpy associated with this, with the hydrogenation, is 74 kilojoule per mole of hydrogen. Reaction enthalpy is 133.4. Now, what does it mean to have a reaction entropy like this? It means that the equilibrium pressure, so that pressure above which you absorb hydrogen and below which you desorb hydrogen, is 1 bar at 283 degrees C. Now, magnesium is also reversible, can absorb and desorb hydrogen in a reversible manner when it's catalyzed with some additives. However, let's focus now on the reaction enthalpy. So we saw that the reaction enthalpy leads to have an equilibrium pressure of 1 bar at 283 degrees. However, for practical application, this is a value of enthalpy that is rather high. The best value for an hydrogen storage material lays between 10 and 60 kilojoule per mole. In reality, nowadays we see that this value is between 20 and 35 maximum, because if we want to couple with the PM fuel cell, you have to have an operating temperature that is, let's say, below 100 degrees C. And that can be just achieved with a metal hydride system that has a reaction enthalpy that is around 30 or even less. Now, so our material, in this case magnesium hydride, is too stable. Good. So what can we do? This is a nice graph published by Berube and shows how the dimension of the particle of magnesium influence the reaction enthalpy. So you can see here that going down with the particle size for different shape of particle, your enthalpy of the reaction, so the formation of the reaction enthalpy associated with the formation of metal hydride, decreases sensibly when we go below 15 nanometer of dimension, and in particular decrease quite fast when the particle size becomes smaller than 5. So now what we have to do is to try to decrease the particle size for magnesium hydride system. So this is possible to do through 3 different methods: nanostructuring, nanoconfinement, and the use then of nano additives. Let's say nano additives influence only the kinetic properties of the material, but nanostructuring and nanoconfinement, they also help theoretically in reducing the reaction enthalpy. Now, let's speak about milling. Milling is a process that is used in industry and is quite economical and is easy to scale up. Can help us to reduce the particle size, for example, really well to the nanometer range of metal oxide. So that what happens? So we do ball milling of magnesium hydride species. So we have an increment of the surface area quite high. So this leads to a triggering of the stability of the metal hydride itself by changing the ratio between the number of atoms that are on the surface and those that are on the bulk. Moreover, the increase of the grain boundary also contributes to decrease the stability of the magnesium hydride system. The presence of metastable phases also is something that can induce the stabilization of our material. Think that we can, by ball milling, we can move from beta magnesium hydride to gamma, that is a metastable polymorph. And moreover, the lattice deformation, the excess volume that you see here, will lead also to a destabilization of our metal hydride. But there is an issue. When you do ball milling, that it's really nice. You can destabilize your material. However, you cannot obtain a particle size of magnesium or magnesium hydride smaller than 15 nanometer. That was the critical point where really the reaction enthalpy start to decrease very much. And this is because the material will start to recombine itself to coarsen and to stabilize itself. So that is not possible. Moreover, whatever you gain by ball milling after cycling at high temperature is lost in a couple of cycles. So nanostructuring by milling theoretically could help to reduce the stability, thermodynamic and kinetic of your system. However, you cannot achieve the desired particle size, and moreover, the gaining is lost upon cycling. Now, there are other methods like to try to infiltrate your material in nano scaffolds. So practically, you can infiltrate via wet infiltration or melt infiltration your magnesium inside this carbon scaffold, for example, like CMK, and you are able to obtain a particle size that is interesting. So 3 to 5 nanometers. So the area where you see that the stabilization, it's really happening, no? And actually, the process is rather complex. So this is already an issue because to obtain a good loading of your carbon nanostructure, you will need to do several iterations of the infiltration. But then, if you see here for this magnesium hydride infiltrated in CMK nano scaffold with a pore size of 4 nanometer, you can for sure obtain a destabilization compared to the 75 kilojoule of the bulky material. No, fine. So this is true. You can obtain a destabilization. And okay, are we happy? No, because however, we have a system or a process that is extremely complicated, involve the use of solvents that is not environmentally friendly. And moreover, if you consider that you adding the weight of the carbon scaffold, you will obtain at the end a system that has half, in the best case, of the hydrogen storage capacity of pure magnesium hydride. So your material, yeah, perhaps it's nice from the scientific point of view because it has improved the properties, but from the practical application, this is not exactly what we are aiming at. Good. Now, nano additive. Nano additive, as we said before, doesn't help to destabilize the thermodynamic of your system, but for sure help increasing the kinetic properties. So again, normally for having a dispersion of a nano dispersion of your additive magnesium hydride, the most used method is ball milling, and you can add in your system species like non-metal, metal and metal oxide, and allies. They are all effective in destabilizing the kinetic or improving the kinetic of your magnesium hydride system. The best known system is the magnesium hydride plus niobium pentoxide as catalyzed magnesium hydride system. And you can see in this graph here from the work of Barkodarian that for a given amount of time, for a given milling time, varying the amount of additive that you are adding to the system, you can obtain kinetic properties. This shown here is the hydrogenation of the magnesium hydride that improve with the amount of the niobium pentoxide. Now, not only you improve the kinetic properties of magnesium hydride by increasing the amount of the additive, but you can, for a given amount of additive, you can increase the kinetic properties of the material by varying the milling time. As you can see here, increasing the milling time, the kinetic properties of your system improve dramatically. And this is due to the fact that while by milling, not only you're refining the structure of the magnesium hydride, but you're also obtaining a better dispersion of the additive, as you can see here. So we pass from a dimension of the active species, so niobium pentoxide that is around 400 to 500 nanometer, to a dispersion that after several hours, 300 hours, that is in the order of 50. Now, with some other system, you can obtain dispersion of your additive that are in the order of 5 to 10 nanometer. And this also help enormously to generate area where hydrogen can be splitted or recombined in more effective way, but also help nucleating a new species that is formed during absorption or desorption. Now, in conclusion, since I'm running out of the time, I hope I could tell you that metal hydride properties can be altered via nanostructuring technique or by using nano additive. Moreover, metal hydride nanostructure tend to coarsen in particular at high temperature. Now, the use of nanoscaffolding material allow for sure for effective thermodynamic and kinetic destabilization, but at the expense of the hydrogen storage capacity of the system. And the use of targeted nano additive allows for effective kinetic destabilization, preserving the hydrogen storage capacity of the system. However, it cannot do anything on the thermodynamic properties. Therefore, if you want to achieve a thermodynamic suitable hydrogen storage material, you have to act on the chemistry of the system rather than to try later to modify the properties of the material to suit the application. Good, so I believe I'm done with the time, so I thank you all for the kind attention, and if later there is any question, I will be more than happy to answer them.
Claudio, thank you very much for your really interesting and educational talk. I learned a lot. We'll save the questions for the roundtable. Okay.
Absolutely, no problem at all.
Important to keep with time. Okay, it is my pleasure to welcome Robert Hebner. He is currently the director of the Center for Electromechanics at the University of Texas, Austin. The center develops advanced technology, generally in the areas of power and energy, and teams with companies to get the technology into the markets. Important current projects involve transportation electrification, hydrogen and transportation electric power, nanodielectrics, and grid resiliency. Before joining the University of Texas, he spent many years at the National Institute of Standards and Technology, more commonly known as NIST, much of it as a member of the Senior Executive Service, culminating his time there acting as director. Much of his management effort at NIST focused on removing technical barriers to trade. He's also worked in the Office of Management and Budget at the Defense, at the Defense Advanced Research Project Agency, also commonly known as DARPA, and at the Sandia National Laboratory. Throughout his career, Dr. Hebner has been active technically, having authored and co-authored more than 200 technical papers and reports. He is a fellow of the IEEE. He spent 3 years as a member of the board of directors and has served as chair of the board of the Center for Transportation and Environment. His talk today will be on the research to support Texas green hydrogen. Robert, welcome, and the floor is yours.
All right, thank you very much.
We can hear you loud and clear. Great. Yes, we can see your talk.
All right, well, good afternoon. I'm very happy to be with you all for a few minutes here this afternoon. I have a very short presentation to help catch things up, and I'm a believer that there's no such thing as a bad short talk. The other thing that I'm going to do is I'm going to take a totally different perspective than we've been hearing lately, to look at other aspects that are necessary to get to a true hydrogen economy. The point that I'm going to end with, and I hope to convince you of this as we go along, is that as hydrogen advances, it's going to have the local flavor. That is, the advances are going to be contained by cost by exploiting the local infrastructure, and what you have already will affect the cost of production, transmission, and storage, and it also will define the available labor and management skills that are available to help you succeed. Now, this is important because the cost to the world of going to a hydrogen economy is huge. So we can't wait 20 years. We can't invest. We don't have enough money in the world to invest for decades before there's any return on investment. This is going to require us building a system, and to build the system, we need to start with the places where it's going. We need to start at least partially with the places where it's going to cost the least to do it. So that's what I'm going to be focusing on in my presentation today, to show some of the advantages that one might get by looking locally. But I do want to point out, or underscore, and I pointed out, it's been pointed out by everybody, that the world is responding to the opportunity for a hydrogen economy. This is a map put together by Columbia University in New York City, and their researchers, the circles point to areas where renewable energy sources are easily available, and the rectangles are where we already have infrastructure for the use of hydrogen. The thing that really jumped out at us, not jumped out, we actually knew this, we were happy that Columbia found the same thing, is that there are only two places in the world in which the heavy renewables and the use of hydrogen are in close proximity, and those are basically in Texas and the Saudi Peninsula. But we've got a lot of teams that are trying to develop. North Africa definitely wants to provide hydrogen to Europe, as does Chile. Australia wants to provide hydrogen to Japan. So long distance efforts are underway, but the cheapest and first are probably going to be where you have short distances, and one of those is here in Texas. So that caught our attention when we realized that. We're also well positioned to grow. I'm telling you a bit about Texas because the examples I'm going to give require you to know something about Texas, and I'm assuming that most people don't have this intuitive knowledge about Texas. So I'm going to take a couple of charts to just introduce you to what Texas has in this area, and then show you how we can exploit that to get to hydrogen in a less costly way. One of the things is that we have the largest existing hydrogen pipeline infrastructure in the United States already. We are the leading domestic producer of hydrogen, and that means we have an experienced workforce. We have people who know how to build and do things with hydrogen. We have a large presence of the leading hydrogen companies, which means we have corporate leadership. And having corporate leadership, that means we have people who know how to manage companies in the hydrogen space and make money. All of those are important. Because of the opportunity, we have a large academic R&D program. The University of Texas at Austin, where I am, has about 100 researchers working in all aspects of the hydrogen economy. So we have a major investment funded largely by the federal government and industry in R&D for the hydrogen future. Texas is the largest state in producing both natural gas and renewables. We do have a core nuclear power base. I know many of my friends in Europe don't believe nuclear power is going to play in the hydrogen economy. Many people in the rest of the world do, and I'm agnostic. We have it, we can use it, we can make the choice as we go along to see if it makes sense. And we also have the potential for large-scale underground storage. So those are the resources that we're bringing to the table. The other resource that as people do not really appreciate is what we're calling the Texas Triangle, which is this part of Texas that is shown on the screen now. And in that part of Texas, where I have the red triangle, we have a greater population than 35 of the 50 states in the United States. So it's not a tiny section of the United States. This is population-wise is huge. We have the equivalent GDP to that of Russia. So economically, this is a huge area. We have the largest hydrogen pipeline in the United States. And in that area, we produce about 20% of all US hydrogen already. So this is an area that is ripe for developing the hydrogen in the future. So what we said is, okay, how can we take advantage of what we have and start producing hydrogen right now? Because what we would like to do is start reducing the amount of CO2 being emitted. We'd like to start reducing the particulate emissions from diesel trucks. We'd like to clean up the atmosphere in Texas. So what we looked at is that we're talking a lot about hydrogen from electrolysis, and we want to use renewable sources, which are generally wind and solar, and that requires a lot of investment to make things different. What if we just put in electrolysis where we have the use of hydrogen right now and sort of clean up our house before we start doing things new? So what we looked at is the price of electricity in Houston, where we have a lot of gray hydrogen being produced and used today. And what we found is that about 80% of the time, the price of electricity is below $3 per megawatt hour, or 30 cents a kilowatt hour. So the electricity is reasonably inexpensive in Texas. There is part of the time when it does get expensive, but most of the time it's very inexpensive. And interestingly enough, in Texas, because of the amount of wind and solar that we have, when we're down in this region, it tends to mean we have the most renewable energy being used. So what we did is say, okay, how much does it cost to make hydrogen if we just bring in that electricity at that price and make hydrogen using an electrolyzer that I can buy today? And what we found is, as long as basically between a price of about $26 per megawatt hour and 50, the cost is about constant. The electrical energy cost stays pretty flat once we get up so that the cost of we've got the volume up high enough of use, the fixed cost comes down, and we end up with a total cost which is below $2 a kilogram. The United States is committed to get hydrogen at $1 a kilogram, and we can see from this approach we're already below 2. So we're starting to look pretty competitive, and you start looking at what that could do for you. Today we're using steam methane reformation in that part of the state. The problem with that is it has very high carbon intensity. And what we're trying to do is reduce the carbon intensity. If we can use electrolysis if we get 70% efficient electrolysis and use it at a 65% of the time, the production cost is only about $3, is about $1.36 a kilogram. And we have we've reduced by about a third the amount of CO2 that's being produced. As you look at this, you may ask yourself, why does it? It's counterintuitive that if I use my electrolysis unit less, the production cost goes down. And the reason for that is that the shape of the curve of the cost of electricity. When I try to use the electrolysis unit all the time, I have to pay a lot more for some of the electricity that I use, and it factors in. If I can stay in that nice sweet spot and use the electrolysis unit only part of the time, the fixed cost balances, the electricity cost balances, and we end up with a lower production cost. But this was not the only, this is the first thing we looked at to see how can we make hydrogen cheaper and cleaner. The other thing that we looked at was the challenge that the fact that it is true almost everywhere in the world. The people live in this white area in Texas, the wind and solar, and the blue and red areas. So these areas basically are separated by 400 to 1,000 kilometers. And over the last decade, Texas has already invested about $10 billion in electrical transmission lines to move the solar and wind power from where it's produced to where people live. But there's another thing to think about. Let's assume that we wanted to do the hydrogen along the coast where we're using it already. There's two things we can do. One is the one that we talked about earlier, where we take the power, put it into the grid, and produce hydrogen where we need it. The second approach is to make hydrogen right where the wind turbine is, and then use a pipeline to move the hydrogen to where we're going to use it. And Texas is not adverse to pipelines. Here's a map showing pipelines in Texas. The blue lines are those that go to other states. The red lines are those that just stay within the state of Texas. So we sort of like pipelines in Texas. But what we found by looking at which is cheaper, we found that if we reduce the price to just an equivalent of dollars per kilogram of hydrogen, if we transmit electricity, it's almost 46 cents a kilogram of hydrogen. If we make the hydrogen in West Texas and transmit the hydrogen via pipeline, it drops to 14 cents. So it's about a third the cost of transmitting the same amount of energy by transporting it with hydrogen rather than electricity for this particular application. Now, the thing that I really liked about this is it brings in the question of what the future electric grid should look like, because every manufacturer of gas turbines for power plants is now adjusted burn so they can run some hydrogen now and 100% hydrogen in the future. So we may ask, I could see a time in the not too distant future when everyone wants to build a high voltage transmission line. The question comes, does it make more sense to put a hydrogen line to a power plant and just run local distribution? So that we may change the nature of our grid by going to hydrogen if we can get things like factors of 3 in areas where we can get things like factors of 3 savings in costs by using hydrogen rather than transmitting natural gas. I should also point out that we have a tremendous potential for storage in the areas where we're using hydrogen today. This figure shows the city, roughly the city of Houston, but what we also have are salt domes underneath the subterranean salt domes, and 3 of them are already being used to store hydrogen today. And we have a lot of other features that look very attractive for storing large amounts of hydrogen, both offshore and onshore and out in West Texas. So the potential for hydrogen storage is huge. So the takeaways that I want to have this, the simple message that I'm trying to get across is that the most cost-effective solutions will likely build first on local infrastructure. The models and the data that we're developing, the research we're doing should be generic, but the optimal solutions are going to be location specific, and the return on investment is going to be location specific. We need to focus on the production, transmission, storage, and use. And I want to make the point that the research is, and that's why I picked the research I talked about, is more than just materials. Like the other speakers, UT has a major, University of Texas has a major program in looking at the materials, because the materials are the way we're going to drive the costs down, but they're not the only way. So we have to look at materials, but we have to look at all of the storage, transmission, production, and the system aspects and the interaction with transportation and utilities. All of those are ripe for research, and we have to make them all come together at the same time in the same place to make a system that is really going to work. And with that, I thank you for your attention.
Brilliant, Robert. Thanks a lot for that. No need to go so quickly. There's plenty there to think about. Right, I think I'll invite all speakers to turn on their cameras. And please bear with me while I now try to share the questions that have been coming in with everyone. And we'll try to have a quick discussion on those. I have to apologize for the logistics. I've been doing this on my own today, so I don't have a back office to help me out with questions and getting this all organized. Okay, let me see. All right, I'll put this one down. I'll share my screen. Okay. So is my screen visible to everyone?
Yes, it is.
Yes.
And I'm
okay,
sending
great.
you a question in the chat that I just received.
Okay, I'll see if I can get to that then. Right.
Thank you.
So one question that I think came up was, or was mentioned, some work on or shown on stability of electrolyzers. I wonder what comments people can have from the research side and more from the industrial side. Is think it's mostly to do with the operation and maintenance costs of electrolyzers. Is this a big factor that still needs to be overcome? What causes the instability also of the electrolyzers in terms of what are the degradation mechanisms and what needs to be overcome? So I'll leave it. Anybody can answer first if I could see the people. Ah, there we go. Anybody wish to comment on that? No. Vanessa?
Well, I will admit my ignorance. I know that it's a hot topic. I know that we have, I know somebody here at the university who is doing research in it, but I'm not familiar with this research. So it's not an area that I know.
Sure. Vanessa, what about?
I'll endorse the question, but not answer it.
Mm-hmm.
Yeah, so maybe I can just briefly comment about the maintenance. I would say, of course, it's depending on the technology. So, for example, the cost will not be the same if we are talking about PEM technology or an alkaline or different technologies. So it depends and should be studied case by case. And regarding the stability, of course, I think it was regarding the stability. Okay, regarding the electrodes, I think, of course, this again is related to the application of the electrolyzer. So it's not the same if we are operating the electrolyzer in a stable condition, so nominal conditions, so meaning that we are anytime at a constant, for example, a current density or at a constant output pressure of the hydrogen produced. But if we are operating, for example, the electrolyzer in a dynamic mode, the stability of the electrolyzers are suffering quite a lot, I would say. So it's depending on the operation of the electrolyzer. Yeah.
Maybe I can add something. As Vanessa already mentioned, that it is actually highly dependent on technologies. I mean, basically different technology, alkaline, PEM, they have different stability targets. And one of the reasons why, I mean, most of the materials, they are unable to survive, I mean, or they have they don't have a satisfactory stability in electrolyzers is because that electrolyzers, they normally operate in very harsh conditions. For instance, in PEM electrolyzers, I mean the typical pH values is between 2 and 5, and which is acidic. And in alkaline, of course, I mean the pH is also much higher. It's probably about 13, and they are all harsh conditions. And so many materials, they are, well, as I said, I mean, there are already some substitute materials to platinum, but for long-term operation, these platinum group metals, they are still outperforming many others. I mean, these transition metal-based metals, because they have much better electrochemical stability when used in electrolyzers. In terms of targets, I think the fuel cell and hydrogen joint undertaking, they have this multi-annual program where the stability target for each technology has been defined, but I don't remember the exact numbers, but basically for PEM electrolyzers, the expected lifetime is probably, yes, it's about 10 years. And for alkaline is even 20 years.
Okay, thanks, Lifeng. Could you expand a bit on what are the degradation mechanisms? I mean, is there chemistry we could work on to reduce those pathways?
Well, this yes, I mean, as Vanessa mentioned, this also depends on the operation conditions. For dynamic operation, you might have this physical loss of your catalyst, or maybe you have this electrochemical dissolution of your components, for instance, bipolar plates, or the other important degradation is also from the membrane. For instance, I mean, one of the reasons why the anionic membrane is so far not technologically mature is because the degradation of the anion exchange membrane, which can only survive, let's say, for maybe maximum 1,000 hours, which is definitely is not suitable for long-term operation. I mean, up to years. For PM, I mean, it's much more stable. This has been demonstrated. I mean, it can be stable in acidic solutions or environments for maybe 20 up to 40,000 hours. And that's why PM is much more, let's say, or comparatively more mature than AEM technologies. Of course, I mean, under these harsh conditions, not only the catalyst, but also some other materials, as I mentioned, maybe the bipolar plates, the connects, the connectors, or something else, or from the other side, the balance plant parts, they may also decrease over time.
Okay, thanks, Lifeng.
Which will affect the operational stability of the whole system. Yeah.
Okay. All right. I think that's a clear contrast to, for example, the PV technology, which is a recent technology. There are 2 or 3 technologies on the market at the moment, and one is slowly substituting another one, and it's clear what the main technology is. A very hot topic in that technology, which should be taken into account and look at this type of technology as well, is ruggedness and stability. You know, you always have, when you do stress testing, there's a lot of new things which have been found, even with stress testing in PV in the lab, well, in proper testing, you only found things out when you actually went out into the field and did put the modules on the field, and then you saw other mechanisms which you didn't model or didn't test for, because it was a conjugation of different stress factors, and that might come out with these types of systems as well. Okay. Also, another question which is bouncing around is the foreseeable cost reduction in the hydrogen production or electrolyzing, is that just economies of scale, or are there significant barriers? I mean, what I understand with economies of scale is you can gain to a certain point, but when you get to such a large scale, you start monopolizing the market in looking for materials that the costs actually go back up again. So what are the barriers to actually getting to the low costs that we're promising? We hear promised, for example, in the US, down to $1. Is that really feasible, or are there really big hurdles that we need to overcome and make sure that they're clear to everyone?
Well, I'll
Would
take
you like
first
to comment on that?
I'll take a first cut at that and look at it about 3 different directions. Number one, I've got some faith in the U.S. program that we're trying to put in place today, because it looks at a number of things, including trying to improve the scale. But and there will be economies of scale. But let's assume, for sake of an intellectual argument, that the United States succeeds in making green hydrogen for $1 a kilogram in a decade. If you do that, we just did the study that proves that there would be no one who had a solar farm or a wind farm who would make hydrogen, because they can make a lot more profit selling electricity. Hydrogen would be too cheap to make. So you can't do it. You've got to balance supply and demand and the whole system around it. And the other thing that I bring into, that I talk a lot to students about, is in the United States, we took lead out of gasoline to improve our environment. That only took us over a decade to just take lead out of gasoline. And putting hydrogen to support a number of these other things is going to take a long time. We're not going to go from where we are today to a strict hydrogen economy very quickly. But we need to get an economy of scale in demand and in supply, and keep them in balance. And in the U.S., the industry group is very sensitive to this, and they're talking about how to bootstrap supply and demand so that they stay in balance, so that we can get to where we want to go without either killing the supply side or the demand side.
Okay. Thanks, Robert. Anybody else like to comment?
Maybe I can say a few words. I think I really agree with Robert. He's put the case in with a fantastic analogy about food production. First of all, we need to take the whole system. It's not just about generating hydrogen. It's all about other dynamics and how they're interrelated. Just like an old kind of wheel-based watch, where each wheel plays its role, but the overall the watch need to work in time, and then it's a complex process. So like the biology of the body, the generation and point in production is only one factor. So there are so much at the moment we don't know, and I would say probably we probably can make estimates 1%, 2%, but there are so many other dimensions we don't know. The whole in the energy mix itself, there's so many things, not just hydrogen. There's so many things. So all what we can say is based on that. Based on certain factors, this could be the case, but it may not be the case when it comes to the actual scenario in few years' time.
All right. Thank you, Upo. Anybody else like to add that point? Okay, if not, it was interesting when Robert showed the map where there was renewable energy production and infrastructure for hydrogen. And he showed the case for Texas, where there was the rectangle close to a yellow circle. And I just remember reading this news or this report where in Saudi Arabia, they've just signed a big contract for electrolyzers, and here they have the hydrogen infrastructure and they have the renewable, and it's just in exactly the same spot where Robert pointed out in his map. So the low-hanging fruit is already being picked, and I guess maybe Texas will be signing one kind of these contracts in the near future. All right, Robert, you showed the electricity cost curve. And what I've seen predictions for the future is that with the change in the demand for electricity, you might end up with, well, people were first predicting that you might have zero cost or negative cost electricity, but with flexible demand, that might disappear. So it might actually get rid of those hours where electricity is actually very cheap. Would you like to comment on that?
If I understood your question, you're actually looking at deciding when to produce electricity and sell it, and when to produce hydrogen and sell it. Is that the issue that you're focusing on?
You show the cost curve for Texas.
I showed a cost curve, yes.
Yeah, and when you go to, well, people are predicting when you go to full renewables that you'll end up with a slightly different curve with more, maybe even negative costs in electricity, where people will be paying to actually being able to dump their electricity.
Yeah,
however,
it doesn't, right. Yeah, the thing is that, well,
there's a counter argument that might change with flexible demand.
Right, I understand. I think I said, Chris, and I'm also old enough to remember when the selling point for nuclear was it was going to be too cheap to meter. Renewables are never going to become free or negative, and except for part of the day. Some people think that it's going to be negative, but you don't. Any well-designed power system, which is what we're going to have, because the power industry also has to make money. You're going to have very few times when it's really going to be negative, and you can't build a solar plant or a wind farm for only those times when things are negative. You need to build it so you can make money all the time. And so therefore it's going to be in my mind, it's a very interesting question of how that dynamics is going to work, because if you look at the cost benefit curves, it makes sense for a solar farm to either sell electricity or hydrogen, and there's a really narrow range where the two or one or the other may make sense, and you can do some arbitrage, what we call it, to decide which you want to do at what time. And yes, that's when the negative cost of renewables may come in, but we almost never have. The reason we have a negative cost for renewables in Texas is because we don't want to turn off our nuclear plants. And if any one of those made hydrogen, but the amount of hydrogen you make that way is insignificant compared to what Texas needs in hydrogen. So if we took 100% of the negative and even up to a normal, it just isn't enough. That's down in the 10% range, and we've got to get up to a production time of 50 to 60% of the time using our electricity. So we need a better answer.
Okay.
But yeah, it helps that whole, but you're never going to make a business about it with that one activity.
Yeah.
And we have the same thing in Texas because we occasionally have power that costs $5,000 or $9,000 per megawatt hour. But we've done that arbitrarily just to keep the production levels high. So you're never going to make money aiming to just do that either. You have to aim for the middle, or you're not going to. There's not enough opportunity to make enough money to pay for the infrastructure.
All right. Thanks, Robert.
Sure.
Okay. Well, I think we've answered most questions that were placed today. I might have one just for Li Feng at the end, which was, I see this quite often. I'll put it here. Okay, I keep seeing people talking about powering electrolyzers with a solar panel or solar cell. And I always wonder why you just don't connect two solar cells together to get double the voltage.
Well, that's I mean, practically, I think a PV plus electrolyzer is more a realistic approach for green hydrogen production. But the thing is that, I mean, one of the advantages, at least claimed by for the direct solar water splitting, is actually if you can split water just using semiconductor photoelectrodes. And this can simplify significantly the device design or whatever. I don't know, maybe Wolfo can correct me because he also had a lot of experience in photoelectrochemical water splitting. But this is one of what they call, this is a holy grail of this photoelectrochemistry. I mean, it's the challenge is that why this is a long-term goal, I mean, in terms of the hydrogen deployment roadmap, I mean, I think DOE also think this is a long-term solution for hydrogen production, is because that most of the semiconductor materials, they are not electrochemically stable in solutions. You have one of the most challenges is the stability issue again. I mean, you can definitely achieve a good power conversion efficiency. You can produce hydrogen in minutes, in hours, but not in years, because the semiconductors can easily get corroded over the operation. And of course, there are a lot of R&D still ongoing. I mean, trying to improve, for instance, to passivate the surface, to incorporate electrocatalysts with semiconductors in order to improve the overall performance, not only the activity, but also most importantly, the stability. But this is still unmet challenge, I would say, at least at the moment. And I mean, for the PV plus electrolyzer, it's not as simple as, I mean, you have a PV module and you have electrolyzer, you just directly connect them together. You also need to have a kind of converter, and you will lose some kind of energy. I mean, this is also it's not a disadvantage, but more it's more complicated in terms of the design of the device. And photoelectrochemical direct solar water splitting is in this sense is simpler.
Okay.
Maybe I can add a few words to that.
Direct water splitting with light.
I will add a few words to that, Leo. I think I agree with you. The way I would look at it slightly differently, and again, I agree with you 100%. We know how fast the PV cost came down with Chinese PV coming into the market. It's significant phenomenon, and there were times that we were dreaming about PV peak watt hour. Well, cost is about $1, but it's less. It's only 20p or something now. I can't remember exactly what's coming. Is crazy. That's one factor. The second thing is, we know that any technology would tremendously progress if the investment is made. There's a huge investment going on in electrolysis now. So you would expect, obviously there are 6 or 7 different chemistries there, technologies there, but some technologies will advance significantly in the next 5 to 10 years, and cost will come down extremely. And in fact, I provided some data to support that in China, they have already achieved that by bringing down the electrolyzer cost.
Yeah,
so when you couple the
achieve that?
electrolyzers and PV, very cheap PV and cheap electrolyzers, how can you argue anything else against that? There's no chance.
Was that cost reduction just economies of scale, or was there technological breakthroughs to bring that down? Is there really need for research, material-based research for this, or is it just an engineering problem and a financing problem and a policy problem to get electrolyzers to market?
Science and engineering problems are always there, and we know that what are they, and then how overcome and all that. And then maintenance cost is one of the key hidden costs for electrolysis. I don't think people have taken seriously the maintenance cost. We looked at the carbon footprint of operational of electrolysis, and then we realized that there's significant maintenance costs that people don't think about. If you buy electrolyzer from the Sheffield company, which is the forgotten the company name now. So if you buy an electrolyzer from them, they would provide you a service rather than an electrolyzer. They will come and install electrolyzer, and then they'll service it. And that's because it's much more complex. It's just like buying a Rolls-Royce engine. So therefore, there's significant maintenance costs associated with that. And then obviously policy area and then things, they need to be taken into account. But I believe that as the world, as we get more closer to 2030 and 2040, 2050, but politicians will have to respond, and then there's no other way.
Okay, anybody would like to add to that?
I completely agree. I mean, with what Wupo and Robert said previously, I mean, there are many factors affecting the cost, the reduction. I mean, but as a researcher, I would always advocate that this technological improvement or innovation is always very important. That can lead cost breakdown or help the technology to get penetrated in the market. Just for example, as I mentioned earlier, I mean, the AEM electrolysis technology. I mean, if we are able to, for instance, to improve the stability of ionic exchange membrane to the level of the proton exchange membrane, then we completely eliminate the needs for platinum group metals. In this way, we can reduce the costs and also the for instance the energy saving strategies that I mentioned in my presentation. For instance, using a bipolar membrane or using the asymmetric electrolysis strategy. I mean, this can also help substantially reduce the energy input. For instance, from 1 point something or 2 volts down to even 0.5, and then you can also save the utility cost for electrolysis. I mean, the problem is whether these technologies or these material advances or technological advances can be uptaken timely or quickly. So this is I mean, if this can be widely deployed in a timely manner, so I believe that this can also help bring down the hydrogen cost.
Okay, I guess we're coming to the end of our time. Thanks. I guess maybe one data or one graph I'd like to look at or see, which we always see in the PV community, is efficient technologies and efficiencies, how they progress over time. And we see that as a function of number of publications, or we see that as a function of installation which is the learning rate or the learning curve. Do you have any information on how that is for hydrogen electrolysis, production of hydrogen, or other ways? How's the progression been over the last 2 or 3 decades? Has it been rampant like PV, or is it a much slower rate? I guess that's a question nobody's got an answer to. Okay, maybe I could write a paper on that one, get the numbers out there. Because I guess it's also more difficult with electrolyzers is to try to quantify efficiency, isn't it? It all depends on what over potential you're working at and scale.
I don't know.
Sorry, Robert?
Yeah, something I just don't know. I know the general field, but not electrolyzers specifically.
Okay. All right then. Okay, I think I'll wrap up. We've got 5 minutes. Once again, I wish to thank all of you for your time. I learned a lot today, and I'm sure our audience learned a lot. I'm happy to say that our audience, well, the number of registrations was about 200, and today we had about 70 people present, I think, 60 to 70. The gender balance was quite good. We're almost at 50-50, female, male. That's always really encouraging. I just hope that we'll have more women on the panels as well to present their work. I think that's really important. And I'll try to get numbers on the ages of the people attending these sessions, because I think it's important to get young people interested so they can make choices on their future. Once again, thanks a lot, everybody, and I hope to see you soon in person, hopefully.